Hey guys, welcome to Unit 11, Note C. Today we're going to look at titration, a special kind of experiment that's going to help us determine the concentration of either an acid or a base using a neutralization process. So the idea here is we're going to standardize a solution. And you may remember that vocabulary from Unit 8. To standardize a solution means I know its concentration. So knowing the concentration produces a standardized solution. These things kind of go together. So what we're going to know is the titration of the acid, and we're going to figure out is the titration of the base or vice versa. We'll know the concentration of the base and figure out the concentration of the acid. So that's what titration is good for. Basically, we want to take some set amount of acid or base and carry out a neutralization reaction. It's actually important that I know the volume of both the acid and the base in order to get all the data I need for this calculation. Then we want to make sure that we're using an indicator, because in the experiment we're going to be adding one to the other, and so we need to be able to kind of visually be able to tell what the pH is of the mixture. So that's going to require an indicator, which you may remember is something that's going to change color and let you know what the pH is based on that color change. So that's going to be how we can tell when the acid has neutralized the base or vice versa. So there are a few important steps when we go through titration. We're going to start off with a non-standardized, which would mean that we do not know its concentration. That's going to be the purpose of the experiment. And then with that non-standardized solution, you want to include an indicator. Those are going to go together in the flask. That indicator is going to allow us to tell when the pH is changing. Then we're going to add a standardized solution. So you do have to know the concentration of one or the other. And then we're going to go through this neutralization. So if you wanted to titrate an acid, you would always use a base. If you wanted to titrate a base, you would always use an acid. You want neutralization. When we get to the end point, important vocabulary here, we're going to see an indication from our indicator that we have reached that neutral point, the end point. So we're going to be basing our stop adding the acid or stop adding the base, our procedure, on seeing the end point. The endpoint is qualitative. It is a color that we can see and observe off of the indicator. So there are three basic steps when you perform a titration. First of all, you are going to need something called an Erlenmeyer flask. I'm going to kind of draw this out to the side here. So the Erlenmeyer flask is the one that looks kind of like a triangle. Sometimes it has a little bit of a neck on it. Erlenmeyer flask. You always want to carry out reactions in an Erlenmeyer flask because it is designed to keep in the reaction. So we're going to be neutralizing in this flask. And yes, you need to know the name of this flask. In this flask, I'm going to put an unknown amount. Oh, good job. An unknown amount of substance. So let's go with an unknown amount of acid. So I don't know the concentration, I should say. I do want to make sure that I measure the volume, but I don't know the molarity. The other thing that we want to make sure that we add into the flask is the indicator. The indicator goes in the flask. So we could use an indicator like phenolphthalein, a universal indicator, something that's going to show us what the pH is of the solution. Then we're going to use a real fancy, very skinny piece of equipment known as a burette, or burette if you want to be fancy. And this is going to dispense very precise volumes of, if I was titrating an acid, sorry, lost all my colors here. If I was titrating an acid, I would want to make sure that I'm using a base, right? Always the opposite. And of course, this could be flipped. We could titrate a base with an acid. That's something known as the titrant. The substance that's added during titration is the titrant. And that's something I'm supposed to know both the concentration and the volume. So you need to measure the volume of both of them, but the titrant is always the one with known concentration. The unknown goes in the Erlenmeyer flask. So once we have this all set up, then we can start dispensing the base into the acid or vice versa. And then we're going to watch the color change based on the indicator so that I know when to stop. Stopping would be based on the end point. or the point where we reach this neutral solution, where we know neutralization has occurred. Oh, geez. So 3 steps to performing a titration. Okay, so here is a more precise drawing of the equipment. So the burette has all these little markings on it, and the interesting thing about the burette is that 0 is actually at the top. And it goes all the way down to, most of them that I've seen are about 50 milliliters at the bottom, and there is a point beyond which you shouldn't dispense. You want to make sure that you're able to read how much you've dispensed. So the way that this works is if I go from 0 and I dispense dropwise all the way down to somewhere between 20 and 21, I would be able to then measure kind of backwards from reading a graduated cylinder. The markings for a typical graduated cylinder would be to the 10th place, allowing you to estimate to the 100th place, or 2 decimal places. The thing you've got to be really careful of is that your 0 is at the top. So if I go all the way down to 18 milliliter mark, that means that 18 milliliters of solution have transferred from the burette into the Erlenmeyer flask. That means that's the volume that's now reacting with the acid. So a burette is actually designed to have a 0 at the top. So you want to make sure you're really careful when you're reading the burette. Because the burette is so skinny and narrow, it's really difficult to pour solutions into it. So you always want to make sure that you use a funnel when you load the burette. And when you load it, you want to try to get it to be exactly 0 milliliters at the top, which may mean overshooting it and then dropping out a little bit as you go to get it down to a starting point of 0 milliliters, which would indicate you have let 0 milliliters mix with your acid. So to pour out the extra, you would not want to use your intended flask. You may want to use like just an extra beaker or something to get it to the 0 mark. And then when you've got it at the 0 mark and you're ready to start your titration, have your pre-measured, non-standardized solution with the indicator ready to go and put that Erlenmeyer flask underneath it. Something else I want to point out here. You have control over how much base you add. This is something called the stopcock. Its job is to dispense the base in exactly the level or the rate that you decide. So basically this is a plastic stopper with a hole drilled through it. And if you have the hole completely lined up, it would allow it to flow freely. Whereas if you have it so that the burette is perpendicular to the hole in the plastic, then nothing would go through. We would consider that completely stopped, right? And so you can go anywhere in between. You can rotate. This is just a circular rotation so that you can get big drops, little drops, half drops. You can control how much base is entering the acid in the Erlenmeyer flask using your stopcock. So a lot of vocabulary and equipment involved here with titration. We want to make sure we know the proper vocabulary for everything. All right, now about that indicator, how do I know what indicator to use? I've kind of alluded to the fact that there are different types of indicators. We want to make an intentional choice of which indicator to use. So for that, we're going to look at something called a titration curve. A curve is going to show how the titrant would handle a change in the pH, how the titrant's going to affect the pH, I should say. So the titrant, remember, is the thing that's in the burette. So for this example back here, if I had a base loaded up in here, I would want to look at the indicator's effect on the base in the titration curve. So I chose the appropriate indicator for the titrant. Then we're going to dropwise dispense that titrant and measure the changes in the pH. And you're going to get a graph that looks something like this, showing a slow increase in pH and then a steep increase and then slow again, or vice versa. What the equivalence point is, notice that's kind of similar to endpoint. The equivalence point would be the steepest point on this curve. The midpoint of that S shape would be a good estimation of the equivalence point. It could be quantitatively determined. You could find the slope of these points in order to find the steepest point, right? And if you did that, you would be representing exactly where the moles of acid are equal to the moles of base. So this is more of a quantitative point, the equivalence point, and it's only used in determining the best indicator to use in a titration. The endpoint, on the other hand, remember, was qualitative, and it was used in the actual titration itself. So don't mix up those two terms. Endpoint is different than equivalence point. The equivalence point is going to be able to choose the indicator for the titration. All right. Once I have the experiment set up, I run it, I reach my endpoint. What do I do with those numbers? So there are actually 4 steps to a titration calculation. The first thing is you're going to need a balanced equation. Of course you do, which means we're going to be doing a little bit of stoichiometry, just one little mole conversion. Then you're going to look at the molarity and the volume of what you do know, the titrant, and you're going to use that to determine the moles of the titrant. Once you have the moles of the titrant, you can convert that to the moles of what's unknown in the flask because you have the balanced equation. So that's going to be just a 1-step mole ratio conversion. Once you have the moles of the thing in the flask, remember you had also measured the volume of the thing in the flask. So now that unknown in the flask, we can use the moles and the volume, or moles and the liters, in order to get the molarity or get the concentration. And then of course from there, if needed, we could also find the pH. So let's look at an example together. Going through this problem, I can see I have 25 milliliters of an acid solution neutralized by 18 milliliters of a specific concentration of sodium hydroxide. So I like to kind of set up the burette and the flask as a way to organize my information. Whatever I have the known concentration of would be my titrant. And so what I know about my titrant is that it has 18 milliliters, meaning it dropped from 0 to 18. That volume is what ended up in the flask. What I know about what was in the flask originally is that we had 25 milliliters. What made me choose this as the titrant was that I know the concentration of 1 molar. So you start with what you know the most about, the titrant, which in this case is the sodium hydroxide. So using the molarity and the volume, I can find moles using the molarity equation. Molarity is moles per liter, but you do have to be careful because the problem did give us milliliters. So we are going to have to move our decimal back 3 places. So let's plug in the molarity of 1.0. We're solving for moles on the top. And in liters, the volume would be 0.018. So we get a total of 0.018 times 1, of course, would be itself, 0.018 moles now with the first step, using the known concentration and volume to get moles. Now I want to convert the moles of the sodium hydroxide here, mole of NaOH, into the moles of my unknown concentration. Down here I had H2SO4. So how do you convert from one substance to another substance? You're going to need your mole ratio, which means we need the balanced equation. I know I was supposed to do that first. I always think of it when I need the mole ratio. NaOH reacting with H2SO4. So I see an arrhenius base and an arrhenius acid because I have hydroxide and hydrogen ions. So that means the products will be water, H2O, and a salt formed from combining the outside cation and anion, or sodium sulfate. Sodium is +1 and sulfate is -2, so it's going to be Na2SO4, meaning I'm going to need 2 sodiums with my sodium hydroxide. Now I have 2 hydroxides and 2 hydrogens, so that's going to be 2 waters. So now I have my balanced equation for this arrhenius neutralization. This is going to give me the moles of the sodium hydroxide to the moles of the sulfuric acid. So let's start with our moles of sodium hydroxide. 0.018 moles of NaOH. Put that over 1 and then put moles of the sodium hydroxide on the bottom. And we're going to convert to moles of the sulfuric acid. So where do the numbers come from in a mole ratio? Balanced equation. So the sodium hydroxide, there were 2 moles, whereas the sulfuric acid, only 1 mole. So I need to basically cut my moles in half in order for it to be the moles of acid. So it's going to be 0.0090, watch your sig figs, moles of H2SO4. We are almost there. Now that I know how much acid I have, I can compare that to the volume, but you always want molarity. So we've got to kind of convert some of the units again. Molarity is always moles per liter. Now the moles we did just solve for, 0.0090. But I was given 25 milliliters of the acid. Molarity has to be in liters, so we're moving back 3 places. So in liters, this would be 0.025 liters. So now if I take the 0.009 moles and divide it by the 0.025 liters, we get, actually I don't know that off the top of my head, 0.009 divided by 0.025, we get 0.36. Again, with 2 significant figures from each part. Now, because I was solving for molarity, the units are capital M. And that is the final answer. I now know the concentration of my sulfuric acid, which means I have standardized the sulfuric acid solution. I know its concentration is 0.36 molarity. So now you can kind of see why I like to organize it with, what do I know in the titrant? Start there. Convert to what I need to know about the volume or Erlenmeyer flask, and then move into that calculation. So you're using molarity twice, and you're using a mole conversion, basically. All right. So let's use PowerPoint here to recap what I did. They actually started with balanced equation, so where we had the 2 sodium hydroxides and the 2 waters. Then using that, we can find the, well, not even using that yet. First, we can find the moles of the neutralization from the titrant, 0.018 moles, but that was for the titrant, the sodium hydroxide. Then using the balanced equation, we can use the coefficients to get the mole ratio and get half as much sulfuric acid. And then we can use that amount of moles and compare it to the liters, careful with your units, to get the molarity of 0.36 molarity. And if they ask for pH, we could just find the negative log of that number. There is a shortcut. You've got to be careful about what the question asks you, because if it asked me along the way, how many moles or of this substance or that substance, the only way to do that is to go through all of the steps that I just showed you. But if all I need is the bottom line concentration, all I'm interested in is what is the molarity of the standardized solution, I can actually use normality. It is still a couple of side steps because normality is related to molarity, but they're not exactly the same thing. But if you use normality, you can actually set this up kind of like M1V1 equals M2V2, just using N instead of M is going to take care of your mole ratio. So remember, molarity is equal to molarity times the total positive charges, known as the total positive oxidation numbers. So that's going to allow you to basically take care of your coefficients. If you think about where the coefficients come from, when we predict products, we create subscripts off of charges, and then those subscripts create unbalanced equations which later require coefficients. So if we take care of the charges, we take care of the coefficients. There's a specific cause and effect that happens there. Taking care of the charges can be accomplished by just changing molarity into normality instead of having to go through 3 separate breakdown steps. So some people prefer this way. It is totally up to you. You're going to get the same answer, but I want to work one this way as well. So I'm going to kind of use my little diagram to keep me organized here. When I see that I know the concentration, I know I have my titrant, which in this case is the HNO3. What I know about my titrant is that it has this concentration of 0.0750 molarity, and that there are 30 milliliters of it. The other thing that I have is that I'm trying to standardize, so in the flask, this calcium hydroxide. And I measured a volume of 22.5 milliliters of it, but I don't know the molarity. That is the question, right? So starting with what I know, I have molarity and milliliters. To use the shortcut, it can't be in molarity. So I have to convert 0.0750 molarity into normality. Then I can plug it into normality of acid times volume of acid equals normality of base times volume of base. So in order to do that, normality is equal to the molarity times the positive charges. So let's look at HNO3. Hydrogen is my cation, and it has a charge of +1. There's no subscript, so I only have a charge of +1. So for a monoprotic acid, or an acid with only one proton or one hydrogen ion, the normality and molarity are actually equal. So we kind of lucked out there. But now we can use the right units of this capital N. Now let's try using normality of acid, volume of acid equals normality of base, volume of base. So what I just found here, this 0.750 was for the acid, so I'm going to plug that in first. Then the volume was given in milliliters, and for the shortcut, that's fine. We're not using the molarity equation, so we don't have to switch to liters. So I'm going to keep this as 30.0 milliliters. If you want to switch it to liters, go for it. What I'm solving for by using this formula is the normality of the base. But what I know is the volume of the base is 22.5 milliliters. So when I isolate the variable here, it will, by definition from this formula, be the normality of the base. So what do we get when we take the 0.0750, multiply by the 30, and divide by this 22.5? So it's going to be 0.075 times 30 divided by 22.5. And I get 0.1 in the calculator. But notice I have 3 sig figs, 3 sig figs, 3 sig figs. So I'm going to add a couple zeros here and give it the unit N, because it's normality. And notice how the milliliters would have canceled out, but the normality wouldn't have. So that would be my normality of the base, but not necessarily the molarity of the base. So normality is equal to molarity times those positive charges. So if I know the normality of 0.100, I could plug that in. But now I want to consider the positive charges of the base. And the base was the calcium hydroxide, CaOH2. So calcium, being in the second column, actually has a charge of +2. And there is just one calcium, so the total is +2, which means I have a +2 in the formula right here, which actually means to isolate and solve for the molarity, I'm going to need half the normality. So the molarity is equal to 0.05, keeping the 3 significant figures. Molarity. So technically speaking, it is just as many steps, but it's in some ways easier steps. Normality to molarity, as long as you're careful, isn't as difficult of a conversion. And then you don't have to worry about milliliters to liters also, so that's an advantage. The only drawback is this gets you straight from point A to point B. This doesn't answer any questions about how many moles of acid or base you might have. If that's the question, you have to go through the long way, which I showed you before. All right, guys, that's going to do it for titration. I've shown you the experiment itself. I've shown you 2 different ways to calculate the standardized solution's concentration to standardize the solution. So that's going to do it for acids and bases, Unit 11. Our next unit, Unit 12, is all about redox reactions. We'll see you there.